All right, calculus folks, we're on to section 5.2, area. We're going to learn about area under a curve. Okay, now's the time. But first, we have to learn about sigma notation. So before we can do any of this area stuff, we have to establish some rules about how to add up a bunch of numbers and how to use something called sigma notation. You've probably seen sigma notation before. In pre-calculus, when you studied things like infinite series and the idea of adding up a bunch of numbers in, say, an arithmetic or a geometric series. So this may look familiar. We're going to use the letter I here as an index. So you may be familiar with using I as the imaginary unit. We're not using it as the imaginary unit right now. We're using it as an index, which means basically it's like a label that's going to count or keep track of which term in a sequence we're talking about. So it takes only natural number values. That would be numbers like 1, 2, 3, 4, ... Possibly 0, but often starting at 1, at least for our purposes. Sigma notation is this. That's capital Greek letter sigma, and sigma is like the Greek letter S. It stands for sum, just means add up. And then you put the starting value of the index on the bottom and the ending value of the index on the top. For our purposes, a lot of time it's going to be I equals 1 to n, and that n might actually be a variable. But other times we'll put a specific constant there, like 5 or 10 or whatever. And then what you have inside here is some function of I, either a function of I or like a sequence term, a subscript I or something like that. Either of those, they kind of mean the same thing. But what this sigma notation means is it means to add up all of the function values for values of I ranging from 1 up to n, with every natural number in between. So this means f of 1 plus f of 2 plus f of 3 plus all the way up until we get to f of n, wherever n is. Okay, if n was actually equal to 2, then we would have stopped here. If n is equal to 10, then we're going to have 10 different terms that we're adding up for the values of I from 1 to 10. Okay, so you add them all up as far as you need to, and then as you stop somewhere. So let's do a couple quick examples. Let's say, for this first one, let's say we're summing I equals 1 to 5, just I. This would mean I is 1. When I is 1, it's just 1. When I is 2, it's just 2. When I is 3, it's just 3. And then 4, and then 5. So it's just that. 1 plus 2 plus 3 plus 4 plus 5. And this gives us 6 plus 6 is 12, plus 3 more. This is 15. And then let's do another one. 2. Let's say you're summing from I equals 1 to 5, and you're going to sum I squared. Okay, that's going to mean now when I equals 1, you get 1 squared. So that's the first term. When I equals 2, you get 2 squared. That's the second term. When I equals 3, you get 3 squared, and then 4 squared, and then 5 squared. So, add that up. Whatever you get from that, blah, 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 that's your number. I forgot to actually add it up on my notes, but it doesn't really matter. I'm explaining how to evaluate it right now. What we're going to do a lot for our purpose, or for our purposes for calculus here, what we're going to do a lot is something like this. Summing f of some ith x value, and then times a change in x, delta x. That is the type of expression you're going to see coming up a lot this chapter. And so what this would mean, with I going from 1 to 3, it means you're going to have 3 terms. And so this would be f of x1 times delta x, plus f of x2 times delta x, plus f of x3 times delta x. Like that. So we're going to take this exact function, and the only thing that changes is the value of I. So x1, x2, x3. Otherwise, it's the same. So these numbers are going to be different. The function outputs are going to be different for different inputs. You may be able to specify the value of x1, x2, and x3, plug those numbers into the function and get output values. And you may also know, you may also be able to figure out what's the value of delta x, and then multiply each of them by delta x individually and add them up. Or you could just factor out the delta x and add up all your function outputs and then multiply the entire sum by delta x, and that would be fine. So this I hope looks kind of familiar because we did do this back in chapter 2, near the beginning of chapter 2. So before we go on, I want to go over some summation formulas. Okay, so let's go over some basic summation formulas. Here's one that is often kind of a stumper for people. What if you have the sum from I equals 1 to n of 1? The function we're seeing in here is a constant function. It doesn't depend on I, which means that no matter what input you give it, it's going to spit out the same value, which is just 1 every time. Now that doesn't mean that we're not still going to change the value of I for each term in the sum. So when I equals 1, it's going to be 1, because it always equals 1. Plus, when I equals 2, it's going to be 1, because it always equals 1. Plus, when I equals 3, it's going to be 1, because it always equals 1. Plus, and keep going like that for 4, 5, 6, and you're going to keep going until you get to when I equals n, in which case it will equal 1. So what is this going to add up to? Well, it's 1 plus 1 plus 1 plus 1 plus 1. I mean, obviously that's going to be, if there were 5 1s, it would equal 5. If there were 10 1s, it'd equal 10. How many 1s are there? Well, we're talking about adding from I equals 1 up to n. And we have a different term for each value of I. How many values of I are there? There's n of them, right? If you're going from 1 to n, that's n values. So n of these means that this adds up to n. So that is the that is the sum rule that we can use here. Summing I equals 1 to n, 1 gives you n. Okay. We're going to need to use that. Okay, we're going to need to use that. You're not going to have to memorize them, but there's 4 different summation formulas that we're going to use, and we need to know them. Okay, so let's go over the others. So the next simplest one would be summing from 1 to n the number I. So this would be like, for example, 1 plus 2 plus 3 plus 4 plus 5 plus 6. That's what we have here. 1, 2, 3, 4, 5, 6. So this is n equals 6. Okay. So now you can visualize this as adding up, counting the number of dots in this triangle. Okay. And there's a clever way to talk about how to count these. If you take the dots in this triangle, reproduce those exact same dots, but reflect it over, and you get over here. So we have the dots here, and we have the dots over here. This is exactly double the number of dots we want. But how many dots are there now? Since these two triangles fit together into this nice rectangle, we can just take the number of dots in the rectangle, which is kind of like doing the area of the rectangle. This is n dots. This is n plus 1 dots. So it's n times n plus 1. That's the total. But then since we doubled it, you have to divide it by 2. And that is a nice sort of visual proof of this formula. Turns out, if you want to do 1 plus 2 plus 3 plus ... plus 20, all you need to do to evaluate that sum is just do 20 times 21 divided by 2, and that's 210. Sorry, 210. And you got it. So there's this nice, quick, easy formula that you can use to add up all those numbers. This is called a closed form. When you have a sum written out with like a ... in it, because it's going to go from 1 to n, and maybe you don't know the value of n because you haven't specified it, that is, I think they might call that an open form. I'm not sure what that's called, but this is called a closed form. When you compress it down into a nice simple formula of, in terms of n, like here it would be in terms of n. We're going to need to use these in order to solve our integration problems coming up soon. Let's do the others. If you're adding up squares instead of adding up like I squared instead of I, then you can do this thing here. So this is kind of interesting here. What we have is what's the best way to explain this one? We're adding up. Oh, that's right. We're adding up like sets of squares. So the top row here is like 1 squared. Then the next row down, level down is like 2 squared, and then the next level down after that is 3 squared. Okay, so if you stack up like groups of blocks that are squares, like squares, successively larger squares. This is like adding up 1 squared, plus 2 squared plus 3 squared. So this is representing n equals 3. Okay, but you could imagine it making that bigger. What you do is you take 3 copies of that, 1, 2, 3, and you stick them together into something that looks like this. And then you come up here and take the top row and you slice it in half and you flip it over and you make a box. And then again, you calculate basically the volume of that box, n times n plus 1 times n plus 1/2, which is this one here, n times n plus 1 times n plus 1/2, but then you divide it by 3 because you took 3 of them. So there's the formula you get from this example, and that just algebraically is equivalent to this. So this formula for summing is can be kind of proved with this visual thing. And then there's one more. The last one is for cubes. So here again we have n equals 3. We have here's 1 cubed, and here's 2 cubed, and here's 3 cubed. Okay, so 1, 2, 3. What you do is you take these and you kind of split them up. You take them and you split these cubes up into pieces, and then you rearrange the pieces into a big square, and it turns out that this is 1 plus 2 plus 3 by 1 plus 2 plus 3. And this is one of the most shocking ones of all. It turns out that adding up cubes is the same as adding up the numbers and then squaring the entire sum, which is pretty amazing. It only works because you're going from 1 to n. If you're not going 1 to n, then that rule doesn't work at all. But in particular here, we get this beautiful little summation formula, which is the same summation formula we had for adding up 1 to n. You see here, it's n times n plus 1 over 2. Get the same thing, and then square it. And you get the sum of cubes. Okay, so those are 3 summation formulas we're going to use. There's also a couple of properties of summation that we're going to need. And these 3, we're going to do 3 properties here. The first one is basically just factoring. Say you have a constant multiple on your function. Well, you're adding them up, right? So you can, if you got like c f of 1 plus c f of 2 plus c f of 3, you can just factor the c's out and get c times f of 1 plus f of 2 plus f of 3. And that gives us c times the sum of f of I. Okay, so you can pull a constant outside of a sigma, and that's just factoring it out of the sum. So that's the first property. The second property, this is in the textbook. This is not a super important property. This is basically just combining the constant factoring property that we just talked about with this property, that adding up 1 a bunch of times gives you n. Right, so adding up 1 a bunch of times is going to give you n, factor the c out, and then multiply the n by c. So that's kind of just combining 2 rules together. But then this last one is pretty important, and it is that summation, just like derivatives and just like integrals, distributes over addition and subtraction, like this. So here I'm using the sequence term notation for AI and BI. Those are like sequence terms. There could be f of I and g of I, exactly the same thing. Doesn't really matter what notation you use. So maybe it makes more sense to you if you don't remember working with sequences back in college algebra. If you're more comfortable with the function notation, then it would be something like this. Yeah, it's the same thing. And this basically works because addition is commutative. You can take a bunch of things added together and you can rearrange them. So if you've got if you got like f plus g plus f plus g plus f plus g, you can just rearrange them and get all the f's together and then all the g's together, and then add up the f's, add up the g's, and then add those together. It also happens to work if all the g's are negative. Then you can factor out that negative from all the g's and subtract that sum of the g's. So this is the sum and difference property for summation. And I know I said earlier that just like derivatives and just like integrals, summation distributes over addition and subtraction. But in fact, I should point out that the fact that integration distributes over addition and subtraction actually kind of, in some ways, is justified by this fact, and it has to do with, definite integral that we're coming up to pretty soon is defined in terms of a sum. So the fact, like the distributing over addition for integrals, really is justified by this property, which is in turn justified by the commutative property of addition.